Are you struggling to understand deflected shapes in structural frames? In this video, I will show you how to draw deflected shapes, bending moment diagrams, and shear force diagrams using these two examples so that you can master frame analysis without any confusion. Hey friends, if you're new here, I am Dr. Jawed Qureshi, a senior lecturer in structural engineering and design at University of East London. On this channel, we explore structural engineering. Deflected shapes of structural frames is often misunderstood topic, and after watching this lecture, I'm sure that your concepts about deflected shapes will be absolutely clear. Let's dive into today's lecture. First, I will solve these two examples. This is a typical frame with rigid joints on your right side, and on left side we have a frame where we have one internal pin. Please recall that internal pin does not take any moment at all. Let us see how we can solve these problems. First, let us solve this problem with a point load applied at the end, and we have a pin over here. Both supports are rigid supports, which means that they cannot rotate at all. There are four options to choose from. Let us evaluate these options one by one. But before I evaluate these options, I want to remind you of rules that I will be applying and sign conventions that I'll be using. For solving the question, I will be applying these three golden rules. The first rule is rigid joints will remain at 90 degree. For example, there is a rigid joint over here. When you are applying load at the tip, the 90 degree angle, which is here, it does not change at all. It will remain 90 if the joint is rigid. The second rule is that fixed support will have zero rotation. This is a fixed support. Theta over here is going to be 0. So slope or rotation at a fixed support will always be 0. It will not be like that in case of a pin joint. It will be like that. There will be some sort of rotation. Thirdly, internal pin does not take any moment at all. So here we have internal pin. Moment is always going to be 0 at internal pin. After you have applied these rules, then it's time to have a look at sign conventions. Remember, sign conventions are extremely important. If we don't apply them right, then we will get all diagrams wrong. So these are the sign conventions which I will be using. Anti-clockwise shear forces are going to be positive. Tension, it means that arrows pointing away from the element will be positive, and clockwise moments from left are positive, from right anti-clockwise moments are positive. And for bending moment diagram, sagging moments are drawn inside the frame, and hogging moments or negative moments or anti-clockwise moments are drawn outside the frame. Reverse is the case for shear force diagram, when we will draw the negative forces inside and positive forces outside. Remember that anti-clockwise shear forces are positive. Anti-clockwise shear force is like this. It will generate anti-clockwise moment, and it has to be drawn outside the frame. Let us now assess these options. Load is applied rightwards and there's a pin at the end. Let us assess this option first, option A. When you are applying load towards right, this is maintaining its 90 degree, and over here it is maintaining 90 degree as well. Applying golden rule 1, there's no rotation happening over here, which is fine. But why is it maintaining 90 degree at the right end? We have internal pin at right end. Internal pin can rotate freely. It doesn't have to maintain 90-degree angle over here. 90-degree angle is always maintained in rigid joints, but here we don't have any rigid joint. It means that option A is incorrect. How about option B? When we apply load over here, a double curvature is happening over here and a single curvature is happening over here, but the beam is not bending at all. Now this cannot happen in real life. A beam will always bend if you are applying horizontal load. This can only happen if this beam was really a rigid element. But here it is not rigid element, it is deformable. So when we have a deformable element, then it will certainly deflect. But here it is not deflecting. This means that this option is incorrect as well. Now let us assess option C. In option C, when we are applying loading, double curvature is happening on left column and a single curvature is happening in the beam. And here 90-degree angle is not maintained, which makes sense. When you apply loading, this joint is free to rotate. When it is free to rotate, then angle can be any angle. It doesn't have to be a 90-degree angle. And a single curvature is happening over here. So this option looks right to me. So I will say that this option satisfies all golden rules. How about option D? In option D, when you apply loading, this is maintaining a 90-degree angle. So 90-degree angle is happening over here and double curvature is happening in beam, which does not make sense because when you apply loading, only single curvature is happening because this joint is allowed to rotate. Here, this is not allowed to rotate. It means that this option is incorrect as well. Now let us go away and solve this problem completely and let's draw its bending moment and shear force diagram as well. First, let us draw the deflected shape. Now, deflected shape is going to give us really very important information. It will help us draw bending moment diagram. And once bending moment diagram is drawn, then it will be fairly easy to draw shear force diagram. And we will determine reactions as well. So everything fits in together. First, the deflected shape. Now note that you have to determine the direction of reactions here, and also you have to determine the direction of tension. Here, double curvature is happening in column, so tension is on the outside, and at the support, the tension is towards left because this is trying to bring it towards left. It means that the reaction, horizontal reaction, will be towards left. And when horizontal reaction is towards left, then the moment that will cause this column to deflect outwards will be anti-clockwise moment. It means that the reaction moment will be anti-clockwise. One most important thing here is that when we are applying load at the top, this is trying to move the frame upwards. When this is trying to move the frame upwards, then the vertical reaction at left support should be downwards. To bring this frame down, the reaction has to act downwards. Otherwise, if the frame is trying to move upwards and if the reaction is moving upwards as well, then the structure is going to be unstable. And we don't want unstable structure. If the reaction at left side is downwards, then reaction on right side should be what? You're absolutely right. It should be upwards. Other reaction, the horizontal reaction here should be leftwards because the load applied is rightwards. And again, I have to denote notation over here. Tension is happening at the underside of the beam, and here a single curvature is happening on the right column, so tension is towards left. Now the moment that will cause tension towards left will be anti-clockwise moment. Now once I have these reactions, then it will be easy for me to draw the bending moment diagram. Firstly, there will be no moment at left. Remember that positive moments are drawn inside the frame, negative moments are drawn outside the frame. So here tension is inside, so I will just follow tension. So I will draw the diagram inside for the frame. And for column, double curvature, left column, double curvature is happening. So double curvature means that I will draw the diagram like this. So here tension is on this side, and again tension is inside. And this point is point of controflexure, where this is the point of controflexure, which is not visible on the deflected shape. But in case of bending moment diagram, we have point of controflexure at this point. What does it mean by point of controflexure? A point of controflexure is a point where moment is zero, or where deflected shape is changing direction from one curvature type to other curvature. For right column, tension is inwards, so I will draw, and at this point I don't have any moment. Then I will draw the diagram like this. So this is the bending moment diagram. Now how about shear force diagram? For shear force, I have direction of shear forces. Remember, shear force means that the forces that are acting perpendicular to the longitudinal axis of the element. There will be two forces, there will be a couple. When we have two forces, then it will generate either clockwise or anti-clockwise shear forces. So let us draw shear force diagram. Starting from left side, we have leftward force and we have rightward force. This is creating a clockwise shear force. So when it is creating a clockwise shear force, the clockwise, remember that for shear force we draw negative inside and we draw positives outside. So when we have clockwise shear force, a clockwise shear force is drawn on the negative side. So let's draw this shear force. This has to be a straight line. And for beam, we have two forces. One is downwards, other is upwards. And this is creating anti-clockwise shear force for the beam. So anti-clockwise is positive as per our sign convention. So we will draw it outside the frame. So here it's negative. And how about right column? Right column, we have these two forces. So this is creating a clockwise shear force again. So these two forces, they create a clockwise shear force, and clockwise is negative, so that's why it has to be drawn inside. This is how we draw shear force and bending moment diagram. Now you can see that how deflected shape is helping us draw all these diagrams. It is as simple as that. Now what happens if this angle is not internal pin, if it is a fixed joint? Now what happens if this joint is a fixed joint? So you will see it in next example. So our correct answer is option C. How about if I have a fixed joint over here? This will drastically change the deflected shape. Let us see how it can change the deflected shape. First, let us assess option A. So when we apply loading at the top, this will create deflection in beam. And here 90-degree angle is maintained, which is fine. And here we have theta 0, which is fine as well. And Here we have tension and tension outwards, tension and tension at the top. Here we have tension, and on this side we have tension. On top of the beam we have tension as well. Now this satisfies all the requirements. It means that this option is right, but I have to assess other options as well to see that if this option is right or wrong. Let me have a look at this option. In this option, 90° is not maintained at the top, and it looks like we just have a single curvature. This is the deflection of a beam when we have a simply supported beam. It is deflecting like this. It means that it has got theta over here. Now this is incorrect because I have fixed support over here. So fixed support is going to do something that will cause it to have 90°, as 90° is not complete 90°. So that's why, and the curvature is just a single curvature. It looks like simply supported ends. We don't have simply supported ends. So option B is incorrect. How about option C? Option C is incorrect as well because I don't see any reason for axial shortening of this column. We are applying a horizontal load and there is no downward force applied here. So why these columns are shortening, why they are going down? And I don't see that reason, and why this is going up. And this is the reason option C is incorrect as well, because axial shortening in column does not happen. How about option D? Now option D is similar to option A. Only difference here is that the curvature in left and right column is just a single curvature. So single curvature cannot happen when you have two fixed ends. So you have one fixed end over here and you have other fixed end. Some kind of fixity is here. So when you have two fixed ends, and if you're trying to move this fixed end towards right and something is fixed over here, then the curvature should always be a double curvature. It means that you should have tension on this side and tension towards left. Here it's not happening. So for this reason, option D is incorrect as well. So our correct option is option A. Let us now find out direction of reactions and draw the deflected shape. This is the deflected shape and option A is correct option. So first I will write the direction of tension. So here we have tension here, tension at this point, tension at top, and tension, and tension, and tension. When we have tension towards left in column, it will create a leftward reaction, and also because we have rightward force applied at top, so reaction has to be leftwards. This is trying to pull the column up. Vertical reaction is going to be downwards, and because it is leftwards, because the reaction is leftwards, so that's why the reaction moment is going to be anti-clockwise. That will pull the column towards left, and the horizontal reaction at right support will be vertical reaction, on the other hand, will be upwards because we have downward reaction at left. And the moment that will generate this tension will be again anti-clockwise moment. Once we have all this, then you can pretty much draw anything. You can draw bending moment diagram, you can draw shear force diagram, you can establish anything without the need of any calculations. Let us draw bending moment diagram first. Because we have double curvature, we will have moment like this, tension on this side, tension on this side. We have double curvature in beam as well. So when we have double curvature in beam, it will be drawn like this. And we have tension over here. Again, we have double curvature in column. So that will be drawn like this. And this point is point of contraflexion. Point of contraflexion means that where the deflected shape is changing direction from single curvature to double curvature, and it's a point where bending moment is always 0, and we have point of contraflexion over here. So this is how we draw the bending moment diagram. Now once we have drawn the bending moment diagram, then we will draw shear force diagram. And shear force diagram is simple. Remember that sagging moments are drawn inside the frame and hogging moments are drawn outside the frame. And reverse is the case for shear force diagram, where negative shear forces are drawn inside and positive shear forces are drawn outside. And remember, our sign convention was that anti-clockwise shear forces are positive. So here in left column, these are generating anti-clockwise forces, not anti-clockwise, sorry, clockwise. So when clockwise forces are generated, then clockwise is negative. So it has to be drawn like this, a negative shear force. And beam has got anti-clockwise shear force. These two forces are causing anti-clockwise. So anti-clockwise is positive. And finally, on right side, clockwise forces are being generated. So clockwise is treated as negative. So that's how we draw the shear force diagram. Now see here that there is no difference in shear force diagram. The difference is only in bending moment diagram, where the problem solved earlier, we had one pin over here. So due to pin, this entire moment was gone. It became 0. And that's the reason the other diagram remains the same. The only part which was changing is top right corner, where bending moment was 0. You can now watch the entire video series on IStructE certificate in structural behavior by scanning this barcode or going to this URL. It's very useful playlist to watch. And if you want to clarify your basic concepts, watch this series now. You can download the lecture slides by scanning this barcode or going to this URL. And don't forget to subscribe and like the video if you think it added value to your knowledge and understanding.